So, what is forward and backward propagation? So, in neural network, what we do, we try to find out a weight that gives minimum that gives the minimum error or minimum sum of a square if it is a linear, if ms is our loss function. So basically, we try to calculate loss and we try to see can we get some weights at which we our error will be minimum. So basically, let's say this is our cost function. So initialize our weight w1, w2, w3 in random fashion, and then we try to use gradient descent method to reach to the optimum values of all the weights. And how we'll reach there? Because we'll just calculate our cost function. We'll get the derivative of the cost function, and we'll use this on alpha w minus alpha times dc by dw, and this is the partial derivation of the cost function with respect to all the weights. And this fashion we update all the weights. If weights lies on this side, gradient will be positive, and our updated weight will start getting reduced, and will finally reach to this point. Here gradient is negative, so whole term will be positive, and w will be increasing all the time and will reach up to this point. So idea is how to get this w. So what we do a forward pass, we calculate our error, and then we instead of calling it error, we'll calculate the cost function. Okay, and then we take a differentiation of that cost function with respect to w, that weight. If I have to update w1, then we'll take the differentiation with respect to w1. If you have to calculate with the w2, then I will differentiate with respect to w2, and then we'll update weights using this formula. Now thing is that how you get dw1 and derivative of cost function with respect to all the weights. Is it very easy? So basically we need to follow the chain rule. So what we do, so basically let's say this is our small, let's say, neural network. Okay, and this is our small neural network, something like this. Okay, and this is our output layer. This is output x1, this is x1, this is x2, w1, w2, w3, w4, w5, w6, w7, w8, w9, and so on. Now let's say I have to update this weight, this w1. So what I need dw1 dc by dw1. This is what I need. Then I can update that weight. How will update? So w1 minus alpha times dc by dw1. But how I'll get this dc by dw1? So we know that in forward pass input flows, like we take weighted sum of inputs. So this will go like this. I have to get more weights, so let's say w10 and w11. So we'll get, like, we here will calculate first z, then we calculate a. So z will be what? Weighted sum of input, so x1 w1 plus x2 w11. If there is a bias term, then b. And how we'll calculate a will be activation. We have to apply activation function. So we'll put this value inside the z. So let's say this is coming 0.25. So we'll put 0.25 value in our sigmoid function, because here I have assumed that our activation function is sigmoid function. So I will get this a. So we'll take this output, we'll put 1 upon 1 plus e raised power minus 0.25. So this is how we'll calculate output. And then this a will be calculated at both these two nodes, and then this A will again pass to the next node by weighted sum of input. So it will be for first node it will be A1 W3, and the one value will be coming from the second node of the previous layer, so that will be A2 into W6, and it passes like that only. So what we do, weighted sum of inputs, then activation function, weighted sum of inputs, then activation function, weighted sum of input, and activation function. We reach to the final layer. There we get a value. Now we compare that value with our true value. If it's but it's not same, so we try to see that how much is the error, and then we have to minimize this error. So we take derivative of that. So now idea is how to get this dc by dw1. This is actually gradient. So method is like we have to use chain rule. So z depends on a is depends on z over here, and then this a is depends on this. So let's say this is z1 a1, z2 a2, here z3 a3, and here let's say z4 a4. Okay, so how we'll do that? So we'll calculate derivative of z with respect to w1, then we'll calculate derivative of a1 with respect to z1, because w1 depends on z1, z1 depends on a1, a1 depends on this one, and one loop will go like this, the other loop will let it in this fashion. So one loop will go like this, other loop will go like this, one loop will go like this. So we have to calculate all these values to reach to this point. Okay, because here z1 depends, a1 depends on z1, but here this value depends on this one. So we have to get it respect to this one. So we have to get partial differentiation with respect to all this value. But what if we know what is the value of here? Like if we know the zc by dz at any point, so we can calculate gradient very easily. You know why? Because zc, what is dw dc, d cost by dw1 is nothing but dz by dw1 into dc by dz, isn't it? So if we know, so this is how what will go to, will get dc by dw1. So it's very easy if you know dc by dz at any point, and calculating dc by dz is very easy. We do not have to strictly follow the chain rule, although it is compiled from the chain rule, but we do not have to individually go and calculate it. We can easily calculate dc by dz at any node, and then we'll multiply with this term dz by w1, and dz by w1 is nothing, it is the input associated with that node. Okay, you can calculate also, because z is what, w1 x1 plus w2 x2 and so on. So if we'll take dz by dw1, so we'll get x1. Okay, we'll get x1. So gradient will be x1 into dz by dc by dz. So now the main problem is to calculate dc by dz, and dc by dz is very easy to calculate. So what we do, we know at outer layer our dc by d output is nothing but 1 by 2 into O predicted minus true value, because this is why the square term we differentiated, we got O predicted minus O actual, and that is nothing but error. This error multiplied with derivative of activation function is called delta at this point, and this is nothing but dz by dc by dz at this point. Okay. So we easily, if we know this delta from the previous layer, we can easily calculate it by multiplying it with the derivative of activation function. So what we do, we calculate delta at any layer and is equals to weighted sum of deltas from previous layer, okay, multiplied by derivative of activation function. Okay, for sigmoid, derivative of activation function is a into 1 minus a, that is your output into 1 minus output. So if in forward pass, if you know the output at any layer, you can calculate derivative of activation function. You just, if you know a2, it's a2 into 1 minus a2. So let's say if I have to calculate delta at this layer, so what I need to know, let's say this is connected by so many layers, this is delta 1, delta 2, delta 3. I have to calculate delta here. So delta here is nothing but weighted sum. Let's say weights are w1, w2, w3. So weights are what? Delta 1 w1 plus delta 2 w2 plus delta 3 w3. If we multiply with derivative of activation function, let's say a was the value of output, so a into 1 minus a, so this will be delta this. Now what is delta this? This delta is nothing but dz by dc by dz. Okay, now let's say we have to update weight this weight to w naught. Let's say this is x1. So it's very easy now. How it is easy? We know what is gradient. So gradient for this w naught will be what? Gradient for this w naught will be nothing but this delta that we have calculated here, okay, multiplied by input associated with this weight, that is x1. Okay, now we can update this w naught. So w naught will be what? W naught minus alpha times this gradient. Okay, so we can update this weight in this fashion. So what we have seen what we have to do. We have to do the back, when we have to do the back propagation, we have to calculate this error, and then we will multiply with the derivative of activation function. We'll get delta at that layer, and then that delta will flow to the next layer, and so on. This will keep on going. So we can say in forward propagation, input is flowing. In backward propagation, error is flowing. In forward pass, what we do, we take input, we take a weighted sum, we apply activation function. Again, we get output. That output is an input for next layer, and we how we get the input, we calculate z as a weighted sum of inputs, and then again we apply activation function, and this process will keep on going. In backward propagation, we calculate error, and then we multiply it with the derivative of activation function. That will be delta or del c by del z. That delta will flow in the forward direction, I mean backward to forward direction. And how it will flow? So for at any node, it will be weighted sum of deltas from the previous layer multiplied by activation function of that node or that layer, because activation function is same across the layer for all the nodes. So weighted sum of inputs multiplied with the derivative of activation function, that is our delta at that node, and then we multiply it with the input associated with that weight, that will be our gradient. So we can easily update our weights. So we'll do this multiple times, and finally we'll reach at a point where our cost is minimum, and that is our final target, or that is our objective of doing this complete backward and forward propagation.